Alright, we are going to look at, we are still in our lecture video series. We're going to look at complex integration. So complex integration, there are two things that come into, two or so things that come into play here. Now the first one is that we're going to integrate this over a path. There were two types of integral. It will depend on whether you're integrating it over a path and closing it, and also integrating over a domain, which we'll call a contour. So a continuous map can map an interval to a complex valued function. So that map gives, if it's differentiable, you can differentiate it. But sometimes your contour maps several intervals into several smooth parts. And if that happens, you can join those intervals into a finite number of them, and they are continuously differentiable. So your path can be made up of just a number of continuous paths joined together, and then you integrate over that. Now also, you can also integrate over a domain, and in that domain you might have some points where your function is not interval it's not analytic. It's only at those points where it is not analytic that matter. Otherwise, we'll look at a theorem that tells us, which is Cauchy's integral theorem. It tells us that if the function is analytic and you integrate over a closed loop, the integral will be zero. So what will determine your integral is the points where it is not analytic. Those are the points where you will have a non-zero value. So if you are going to integrate over a path, sometimes you might need to do what we call a parameterization of that path. So if your points are x, your points are the general complex valued points. For an interval between A and B, for your parameter t, sometimes we use this t and as a parameter, and we call it the time. So you can trace out a curve by points as the time varies. That tracing is called a parameterization. So as you trace out time, as time moves from A to B, the parameter will move around through the points, starting from A, which is your initial points, to a terminal point. So a contour is either you can have a point or a point zero if it's just one point, or a sequence of smooth curves from one to joined together, where one terminal point becomes the initial point of the next, and so forth. So in that case, you write your contour as being equals to gamma 1 plus gamma 2. And a parameterization of contour is this parameterization, which will give you all the points for each curve, which makes part of that contour. So let's start this by just looking at an example. Here we are. We have that contour in that diagram there. The contour is made up of two straight lines. The line, it's made up of two straight lines. So it's the line from this point down to that point, straight line. Then from that point up to that point, you get another point. Then we have a quadratic part, this curve. I think this is a quadratic. So you are going to a quadratic curve which is given. So we want to find the parameterization of the positive oriented contour, which is the direction that we have traced. We are going around it. Positive oriented. We are going around that path in an anti-clockwise way. That's a positive way. So you want the line by joining the origin, the point 3 minus 1 and the point 1, 1. The point 1, 1 is joined back to the origin. That's the red line by the parabola y equals to x squared. So there are three parts to this. There are three segments which make up this contour. So there are three parts there which make up that contour. So let us start to look at how we can parameterize that. So the first one is just a straight line from the point joining the origin and the point -3 and 1. So you can get the equation of that line in a straightforward way. The gradient of that line is -3 minus 1 over 3 because it's negative. You just find the change in y, the change in x over the change in y, multiply by that. So it's your usual equation of a straight line. So in this case, we have a relationship y is equals to -1 over 3x. It's a simple starting point. You can start with that and let x be our parameter, because if x varies, we can trace y through this equation of the straight line. So we let our parameter be x, and note that that x varies from 0 to 3. So we use that, and then we use that as our parameter. So we are going to use this equation for this equation of the straight line and that. So if we now want to trace out our z, our points, the real part is x, which is our parameter t. The imaginary part is -1 over 3t, because x is t. So it's -1 over 3t. And the variation is from 0 to 3. So that gives us the parameterization for the first part is t -1 over 3t. Now, the second one is also a straight line. It's joining the point -3, 1 and the point 1, 1. You can just quickly get its equation. The equation of that line is y, by just doing the usual gradient kind of a thing of getting an equation of straight line. It will obtain that equation is y is equal to 2 minus x. So again, this time, we want the parameter to range from 0 to 1. And the line is traversed backwards because your x will range from 3 to 1. It's going backwards. And your y is going to range from -1 to 1. -1 to 1. So when t is equal to 0, it should give us the initial point. And when t is equal to 1, you should get the terminal point. So when t is equal to 0, we're at the point 3 minus 1, and when t is equal to 1, we're at the point 1, 1. So in this case, you can get the parametric equation of a straight line is given by this. So if your equation passes through the point x naught, y naught, so you can parameterize your x as this. Your terminal point is x1. Your initial point is x naught. So you look at the difference between the 2 points, and the parameter is this. You can parameterize it by t, but this one is going backwards. That's why we have 1 minus t. Now this will take care of the initial point and the fact that you are going backwards. So when t is equals to 0, it will be 1. When t is equals to 1, it will be 0. So you will not have this. When t is equals to 1, this will be 0. And for y, you also do the same parameterization. But this one, observe what is happening here. This one is going backwards. Y is going forward. So this one will leave it as it is. When t is equals to 0, you're at -1. And when t is equals to 1, you get the other one. When t is equals to 1, this will be 0. You're at the terminal point. Now, you substitute for the values that we have. The y naught, x naught, and y naught. For x, you get this equation, which is 3 minus 2t. And for y, you get this equation. For y, you get this equation, which is that just equals to, so we've substituted here for y. So y is equals to y plus 1. Y is equals to 1 plus 1 minus t, which is y 1 minus 2 plus t. So the parameterization of that curve is, the real part is this, minus 1 plus 2t, plus the imaginary part is 3. And your z is, your parameter is between 0 and 1. You could have used a different parameterization. Our parameterizations are not unique. We would have used the same, but you are remembering the fact that x is changing from 3 to minus 1, going backwards. We would have used that. But this one is a convenient way of doing this. Usually we prefer using a parameter between 0 and 1. It makes life easy, as we'll see later on. Now, on the parabola, the line, the part which was read in our curve, x is traversed in the opposite direction. It's going backwards. So if t is the parameter, we want it to be between 0 and 1. We want it to be, when t is equals to 0, we should be at 1. So we use this 1 minus t. And y is given by x squared. So the x that we have, which is going back, this x, when t is equals to 0, you will be at 1. When t is equals to 1, you will be at 0. So this clearly gives us the coordinates points in terms of x. And if you want what we have in y, we know the relationship is y is equals to x squared. So it's just equals to 1 minus t. You square that. Then the parameterization is given by this. So the parameterization is given by z. Z equals to 1 minus t, the real part plus the imaginary part, because 1 is equals to t. So the parameterization is just the parameterization of this is 3 parts. So it is the part for the 2 straight lines in the parabola. Now, let us go to the next part here. Now we want to make use of these parameterizations. If we want to make use of the parameterization to get part integrals. So here is how we define our contour integrals over a number of points. So if you have a directed curve, your function, express it in terms of the parameter t. And then you have, it will be a real part plus an imaginary part. Then the integration of this with respect to t is just the integral of the real part plus the integral of the imaginary part. If this is continuous, then the integral along your given path, the path integral, is just given by f of t d gamma dt. So here we use a kind of like the chain rule kind of integration. So these two will cancel out, and you have the integral in terms of this. If it is closed, you have this integral. If the integral is closed, then you indicate it by a circle on the integral. So these are our path integral. And if there are parameterizations now, you can do it in terms of, you can do the integration in terms of t. So this is your z, which is your parameterization. You multiply it by the derivative of the parameterization. That's just the kind of the chain rule which you have. Now, if your function has been expressed in terms of its real and the imaginary part u and v, you just have now this. You just expand this one out, and your integral will become this. You just have expand z dash, is dx plus I dy. If you substitute into this function, this being uiv, you end up with your integral having 4 components, 2 coming from this, 2 coming from there, and you multiply them out. and your integral will be this. So the integration becomes straightforward if you have a contour. Now, for the contours, if you are integrating it over two contours, these are just properties of path integrals. So a linear combination of your integrals is the integral of a linear combination is the combination of the integral. It's a linear combination of the integrals. And if you integrate it in the opposite direction, which you are indicating by minus gamma, the integral becomes negative. And if you are integrating it over several integrals, several caps, several parts of the segment of the contour, you integrate over each and every part of that contour. So this will be what we will do here. Here we are going to integrate. We are going to integrate the z bar plus I times the real part of z. Z bar is the conjugate plus the real part, where gamma is the contour in the last example. So we'll use that in parameterization which we obtained earlier on. Use that parameterization which we obtained earlier on. So the parameterization we have it. So we are going to integrate it over the three parts. So it will be over C1, which is the straight line going down from the origin, and C2, the straight line coming down, starting down and going up to connect with the path, the parabola. C3, you integrate it over the parabola. So what we are going to integrate, the integrand is just the conjugate plus I times the real part. So it becomes this in terms of x. Now this in terms of x, we can just substitute for x. We will look at each part now separately. Now for the parameterization over the first integral, you substitute for x and then y. So if we substitute into this, our x becomes this. The integrand becomes this. Our parameterization is t minus 1 over 3t. It becomes this. So you need to differentiate this with respect to t so that you get what you're going to integrate with. So if you do that, this will come out as this is a constant. It has no x. It will, if you differentiate this with respect to t, it will be 1 minus 1 over 3 minus I over 3t. It's constant. It goes out. What remains is this part, which you are going to integrate with respect to t from 0 to 1. You're going to integrate it with respect to t from 0 to 1. And if you integrate this from 0 to 1 with respect to t, you get this. It's just a simple case of integrating that. So the integrand, the integral over the first part evaluates to 1 minus I over 3 times 4i plus 3, all divided by 6. We go to the second part. On the second part, this is the parameterization. The parameterization is 2t plus I times 2t minus 3. That's the parameter. You differentiate it once with respect to t. And then if you differentiate it, you factor out things which are going to be out, and then the rest which remains with respect to t is this. And you are going to integrate this with respect to t from 0 to 1. If you evaluate that integral, it becomes minus 4 minus I. So what I encourage people is to get your pen and paper and try to work out so that you follow what is happening in this slide. In this small slide, we cannot put all the details. We can, but it will become bulk and unnecessary. So you work it out, and then you get this. Now the last one is the interesting one. You are going to integrate over this contour. You are going to integrate this over this contour. You are integrating between 0 and 1. The parameterization is this. You differentiate it with respect to t. So when you differentiate this with respect to t, multiply it to the representation of the function. The function, where what we are just doing is wherever we have x, we are substituting for the x representation. And wherever we have y, we substitute for what y is in that. And if we integrate, there's a lot of work that you do here. You integrate, substitute for t equals to 0, and then get t equals to 1. You end up with minus 5i plus over 6 times 2. Then, to get the actual integral, is you sum up this whole thing. You sum up this whole thing, and it will give you that. The integral is minus 65 over 18, and then minus 78 over 18i. That's the imaginary part. So that's the path integral of the function z bar plus I, real part of x, I, a real part of x over the contour that were given earlier, which were parameterized in the previous example. So that's the integral. Now that's how you do path integrals. And that's how you do path integrals for complex varied function.